calculus, we're going to work with particle motion problems, and just so you know, we can have particle motion problems along the x-axis, y-axis, and we can also talk about any kind of like horizontal or vertical movement. And the whole premise of this is to make connections between position, velocity, and acceleration. So the first thing, and why I'm starting with the answer key here, is because I just like to have the formal definition instead of struggling to write through it and like maybe missing a key word here or there. Is there's a big difference between an average velocity versus an instantaneous velocity. If you're thinking about driving around in a car, let's say you drive 60 miles in 1 hour. Well, your average speed is 60 miles an hour. You're not necessarily going 60 miles an hour the entire time. So there might be times that you're, stopped at a red light where you're going 0 miles an hour. That's your instantaneous velocity. And then maybe you get on the interstate and you're going 75. I don't know if you got speed or not. But, you might make up for the average velocity, making up for the time when you were stopped by picking up the speed at other times. So the main thing is think of the average velocity as being the average rate of change. And it seems to make more sense, at least to me, that if you think of it that way, that it's the secant line from the endpoints or whatever values that they give you. Whereas the instantaneous velocity would be the derivative of the position. I like that he uses P for position. I've seen books use S, and I think you guys know my S's look like 5s. Maybe yours do as well. So some books use S for position, but I like that this author uses P. And I might go back and forth because I'm so used to using S. So let's get into some of the problems. So we're given this equation, and by the way, you'll notice that we go back and forth to calculators, where you might even use, just make sure that you're in radians. By the way, you could do this without a calculator. Just you might as well practice understanding how to do this because we have the product rule in here, so we could do the derivative without. But you don't even need the derivative for the first problem, which is average velocity, which is saying do P of 3 minus P of 1 over 3 minus 1. So it's clearly going to be divided by 2. It's just a matter of, I don't expect you to know sine of 3 in your head. And that's what I mean by using your calculator. Probably intelligently is a good way of saying it. So e to the t power, whoops, wrong button, times sine of t. As I mentioned, make sure you're in the right mode, or in radians. So I already have that typed in. You might want to double check you type it correctly. I know it's t's, but we only have x's in our calculator. So now I can go back to my home screen and hit alpha trace to grab that equation, do y of 3. And you can write it all out, or because we wrote that equation, I think we would be fine getting our point for the correct equation and trust that that is correct, 0.547. And then divided by 2. And I would leave it in the calculator, make sure you do this correctly. So you don't want to round until the very end, so 0.274. And pay close attention to the units. They tell you that P of t is measured in centimeters, and because we found the average velocity, it's got to be centimeters per some unit of measurement in time, I guess I should say, centimeters per second. So that is average from the start of 1 second until we get to 3 seconds. But then when we get to the instantaneous rate of change, then that would be saying to do P prime of 1.5. And you may have noticed, because I'm making these videos all in succession, that I already had derivative of the first equation written as my y2. I've had students that go to their calc test with this already saved in just because they didn't want to forget. A good moderator would delete your calculator or make you clear it out, but most do not. I shouldn't say that because I'm never in a room for a math test, not allowed to be. But none of my students have came to me and said like, hey, they made me delete programs in my calculator, and maybe they do for you. So make sure you're familiar with writing that. So back in the home screen, I just want the second equation to find the derivative. I believe it was 1.5. Yep. 1.5. We get 4.787. About. And it's the same units, because whether it's instantaneous or average velocity, we should have the same units because it's representing velocity. It's not until we get to acceleration. Well, let's go to the answer key. So it looks like we're going to be doing that again. You can double check that I have the right things. And looks like he actually found the derivative using the product rule, which is good practice. But notice he had to go to a calculator anyway, so you might as well, if you have to use a calculator anyway, you might as well just use it to get the right answer. And I already mentioned this, but it's worth repeating. You might want to pause the video and copy this down. If you think about slope of the secant line, that's the average velocity. Slope of the tangent line, that's instantaneous velocity. So there's a connection between position and velocity, and it's the derivative. There's also a connection between velocity and acceleration, and it's the derivative. So what I'm trying to get at is that the second derivative of position will find you the acceleration. And if anybody's taken physics, you may have learned that already. And maybe you haven't, or maybe the physics curriculum is a little bit different than what I took when I was in high school. Anyway, the derivative of position is velocity. The derivative of velocity is acceleration, which means, like I wrote this out for you, is that the average acceleration is the slope formula for velocity. That's a good thing to notice. Yeah, so we have the same equation as we move forward. So again, pause the video before I go back to the notes. And what we're going to do is find the average acceleration on this. So remember, the average acceleration, the time is still the same, 3 minus 1. But now it is v of 3 minus v of 1. And that's why I think you might as well just use your calculator, because that would be so much work if you had to do the product rule and plug in 3. Because to me it makes so much more sense to just hit alpha trace for that second equation of 3 minus to get negative 20.806. Divided by 2. I mean, you should be putting squigglies because we are approximating, we are finding the average. And wait until the end to actually round, so negative 10.403. So since acceleration is the derivative of the derivative, we add a unit to the seconds. And some people say centimeters per second. I typically just say centimeters per second squared. Because anytime you do the derivative, you have to add a unit to the time that we have. So the difference now is if we want, sometimes we write a of 1.5, then you might want to say, okay, well that's b prime of 1.5, or p double prime of 1.5. So as I go to my calculator, what I'm going to do I'm going to use a calculator. Go to y equals and just make a third equation, which is the derivative, that was the 8th option, by the way, of the derivative equation. So notice I'm changing it to the derivative of y2. I'm just doing the derivative of the derivative when x equals x. So when I go back to my home screen, I can just hit alpha trace for my third equation. And I believe it was 1.5 again. And I got 0.634. And for the sake of making sure that we have good units, acceleration is centimeters per second squared. There we go. I believe if I share the answer key with you, he's going to go through all of that work. So literally found the velocity instead of what I did. And I mean, you're going to use a calculator anyway. You might as well use it to find the derivative. And then you don't have to worry about it. And you're probably getting points just for saying that a of t is equal to v prime of t. And if you want to get points, you can even write p double prime of t is equal to that, which is everything I did. So pause the video if you want to show all of this work. Otherwise, I'm going to give you the next parts of the notes. And I'm just going to talk you through it. And then you can, you'll have them in your notes. That'll be perfect. So, just a reminder, position, sometimes I write S of t, P of t for position. So that's f of x. F prime of x is corresponding to velocity. And then the second derivative corresponds with acceleration. So earlier in this class, in this school year, we talked about there's a connection between the first derivative and the original function. And so the whole premise is we can also make the same judgments. You may remember this chart from before. Is I think this said f prime of x and this said f. Well, now it's velocity and position. The difference, though, is if we're moving along the x-axis and you have a positive velocity, we want you to distinguish that that particle is moving to the right in the positive direction. Now, one thing I do need to mention is sometimes they talk about along the y-axis, so that would be up and down. So if they have the particle is on the y-axis, a positive velocity would be moving up. Okay, so we may encounter problems like that. You never know with AP. They change it every year. It's typically the x-axis, though. That's why all of this is about the x-axis. So notice all of these things. If the velocity is 0 or undefined, there's a potential change in direction. It doesn't have to, but it's potential. So negative velocity is moving to the left. If the velocity changes from positive to negative, that means the particle moves to the right and then to the left. Changes direction, a good way of saying that. And it's more specific, because if the velocity changes from negative to positive, then the particle will move from the left to the right. And then acceleration, there's a connection between acceleration and velocity. And it's all the same. Notice it's potential change in sign of the velocity, because if the acceleration is 0, it might stop accelerating. Think about being in a car. When you press down on the gas pedal, you're accelerating. And then if you let up on the acceleration, you could still be moving forward for the velocity, but the acceleration would be 0. If that makes sense. Anyway, if acceleration is positive, the velocity is increasing. If the acceleration is negative, the velocity is decreasing. All of these should be the same. And I think I've run out of time. And I believe I will see you in the next video.